Place a box on top of an inclined plane. What would be the outcome? It may continue in its new position or slide down the inclined plane. Are there any other possibilities? Yes, it may result in tipping of the box. If we are adding a set of wheels to the box, it will roll down to the bottom of the inclined plane. But in certain conditions, even with the wheels, it may slide down the inclined plane. When do these happen and why? Let us review these actions in detail. Case 1. The box is resting on the plane. The self-weight of the box is acting downward. This can be resolved into components perpendicular and parallel to the inclined plane. The perpendicular component will be W cos theta and parallel component will be W sin theta. Frictional resistance will be developed at the contact location and the same will be matching with parallel component W sin theta. Normal support reactions will be developed at the bottom surface such that resultant will be matching with perpendicular component W cos theta. Thus, force equilibrium is maintained perpendicular and parallel to the inclined plane. The parallel couple result in redistribution of the normal support reaction such that resultant is forming a counteracting couple with the vertical component. Net moment is 0 and the box is in equilibrium. We know that composition of perpendicular and parallel components yield the self-weight W and the same will be acting at the center of gravity. Similarly, combining the frictional resistance and normal reaction yield the net support reaction. So, in simple words, if these two resultant forces are of equal magnitude and are having the same line of action, the box will be in equilibrium. Case 2. The box is sliding down the plane. With increase in slope, the parallel component of the self-weight increases. The frictional resistance developed at the bottom also increases in magnitude such that force equilibrium is achieved in that direction. This process continues until limiting static friction is developed at the contact location. As the parallel force couple increases in magnitude, the normal reaction developed will be moved further away such that moment equilibrium is maintained. The limiting angle until which a body sleeps on an inclined plane is called angle of repose, phi. Any further increase in slope increases the parallel component. However, frictional resistance cannot be increased beyond the limiting static friction and motion is initiated. Instantly, the frictional resistance reduces to dynamic friction and net force results in sliding of the box. We have seen that tan phi is equal to the coefficient of friction mu. Details are covered in a separate video, suggest watching the same for clarity. So, depending on the coefficient of friction between the surfaces in contact, sliding of the box initiate at different angles. Case 3. Tipping. Let us consider a condition with higher coefficient of friction and start observing the same from a lower angle. Summation of forces and moments are 0 and the box is in equilibrium. As the slope increases, the parallel component of the self-weight increases and accordingly the frictional resistance. This results in bigger parallel force coupled in the clockwise direction. The normal reaction will be moved further away such that moment equilibrium is maintained. As seen in case 2, the process continues until frictional reaction reaches the limiting value. But in certain conditions like this, the normal reaction reaches the extreme edge of the object before the limiting static friction is achieved. Beyond this, the restoring moment do not increase. However, as the limiting static friction is not reached, the overturning moment increases with further tilt. This results in tipping of the object. So, tipping is happening at a lower angle as compared to sliding. Again, in simple words, tipping occurs when the line of action of the cell plate moves beyond the extreme edge of the object. Let us go back to the limiting scenario as per case 2 with a lower angle of repose. We have seen that for this condition, any further increase in slope result in sliding of the box. Consider trimming the forward edge of the box. Assume no weight and center of gravity changes with trimming of the box. As the frictional force is independent of area of contact, same frictional reaction will be developed and force equilibrium is maintained in that parallel direction. However, the line of action of the normal reaction cannot be outside the box. In order to correct this, the parallel component of the cell plate need to be reduced. This is achieved with a reduced slope of inclined plane. With this, the parallel component as well as the frictional reaction is reduced such that normal reaction is moved back to the edge. Again, summation of forces and moments are zero and the object is in equilibrium. Any further increase in slope result in increased magnitude for the parallel component of the cell plate. The frictional reaction also will be increased as the limiting static friction is not reached. However, as the line of action of the normal reaction cannot be moved further away, there will be a net overturning moment in the clockwise direction, which result in tipping of the box. For this scenario, the distance to the forward edge remains the same for the condition after tipping as well. So again, tipping will be happening about the forward edge. But this time, the line of action of the normal reaction is well within the outward edge of the object and no tipping will be happening. Let us trim this edge as well. So, the 2 times tipping process happen again. Now, continue trimming the other 2 corners such that object has a symmetrical shape. With this, object placed on the inclined plane with any of the phases result in tipping. Thus, the object placed at this angle result in continuous tipping. It can be seen that with a reduced slope, the line of action of the normal reaction is well within the outer edge of the object and tipping do not occur. Again, trimming of the corner result in tipping. Trimming of all the corners result in continuous tipping of the object. With lesser and lesser dimensions of flat bottom, continuous tipping is happening at lower and lower angle. Isn't it similar to rolling? For perfect rigid bodies in contact, the dimensions of the flat bottom is a measure of resistance to rolling. The static friction developed until tipping is contributing to the resistance. In the real world, actual rolling resistance is derived from various factors. Let us discuss the same in another video.